where was the Z-test at? Where did we click on?
Stat.
Stat.
Z-stat.
Z-stat,
Z-stat.
one sample,
One sample.
and
With data.
With data. This time we gotta backtrack, cause we're not doing the Z-test, we're doing the what?
T-stat.
T.
So now, that's right, so we need to come down to what? T-stats, one sample with data, correct. And notice, like, you know, when you do the T-stat, you see the two sample, we're gonna cover that. You see that paired, we're gonna cover that. Those are on the list, so we're gonna cover them, okay? So we're gonna choose with data, T-stats, one sample with data. So let's select that. Okay. Click on total winnings. We're not, nowhere, no group by, we're good. Here, what goes here? In this, instead of 0, we're gonna put what?
37,318.
37,318, right, the claim population mean, that's right, 37,318. We said we're doing a right tail test, right? So what do I have to change here?
Greater than.
Greater than, that's correct. Ooh, y'all so smart. Alright, we're gonna hold off on the confidence level. What was the level significance 5%?
Yes.
5, okay. So let's check that off so that we know. Let's just check that off. Okay. Now, if you want it, by the way, we skipped this, but just for the record, take a look at these, okay? If we wanted StatCrunch to draw the t-distribution and like tell us where the p-value, the area under the curve, which represents the p-value, we could choose that p-value plot. It's not worth it. I'm telling you, it's not worth it. Well, we could. Actually, let's play with it. Hold the control key down and turn that on. Let's
So
play
what-
with it. I'll show it to you.
To which one?
P-value plot.
P-value.
P-value plot. Now, remember we covered histogram, dot plot, box plot, remember that? So if we wanted to turn those on, let's turn them on. Turn them on. Let's turn them all on. And then finally, down here, we're not going to do the Shapiro-Wilk normality test, but I do want you to click on QQ plot. Remember, that's the normal, we covered that. That's the normal probability plot. But the Shapiro-Wilk normality test is a hypothesis test that would tell you if the data came from a normal distribution. But we're going to look at the QQ plot, all right? Okay, and if we wanted to put a title, we could, but we're not. We just want to look at, we're just reviewing. We're not going to. And then hit compute. Click on compute. All right. Now, you see that? Look at this sample mean. The sample mean was only what? 34,223. What does that mean? No pun intended.
That was the average of those?
What was the claimed mean? The claimed population mean?
37,318.
37,318. Look at that sample mean. That means what? Well, the average of those 17 observations was 34,223. What were we arguing? Look at the known alternative. Look at the alternative. What were we trying to argue? That the true mean is actually what? That the true mean was actually greater than $37,318. We were trying to argue that.
We were wrong.
But look at the sample mean. What does that mean? What does that mean? We didn't.
Prove that it is.
Hold on. Shh. Say it again.
Not enough data. Not enough samples.
I thought you were going to say it. You're
Not
close.
enough evidence.
Yeah. Yes. But I'm looking for the definitive. Like, I want to see who's really looking like deep into this. Yes, we don't have evidence. Look at the p-value. P-value is 0.78. We don't have, right, that's poor evidence. But we didn't even have to go to the hypothesis test. Look at this. Look at that. We didn't even say it. We we failed to reject. But I'm saying we didn't need to even go to the hypothesis test because we didn't
Proof?
Mean didn't even reach the hypothesis.
Yes, so that means, okay, y'all, look, when you do a hypothesis test, it's like you're having an argument with someone. I'm having an argument. Someone said, no, contestants made on average, $37,318 when they get on the show. We were arguing that no, we believe that your contestants are making more than that on average. And we collected those 17 contestants and we calculated a sample mean of $34,223. And that person that I'm arguing with said, well, what do you think that person's gonna say to me? You're debating me? I'll tell you the answer I was looking for. You don't have an argument to begin with. You have which is, we failed to reject. Look at this. You don't even have an argument.
Because you don't have
Why are we talking? You see what I'm saying? You are telling me, you're trying to challenge my claim, and you believe that the true mean is higher. The evidence you collected, you don't even got a damn argument. Do you see that? There's no even purpose of going into the hypothesis test. You haven't shown evidence. This is not evidence because that value is what? It's not greater than $37,318. Now, if that was $39,223, now we can have a debate. Now you got some point. You understand what I'm saying? You don't got a fucking point. you haven't brought any evidence. So of course, if we haven't brought enough evidence supporting our claim, definitely we're going to end up failing to reject the null hypothesis. Is everybody with me so far? All right. In fact, you brought evidence that the true mean is could be less than $37,318. Is everybody with me so far? But nonetheless, let's do the hypothesis test if you don't mind. Okay. So, can I use this space back here? I can sit on his chair.
That's my backpack.
Okay, good point. Good point. So the null hypothesis, we would say mu is equal to, it gives it to you. It's up there. The population mean, mu, is equal to $37,318. The alternative hypothesis says, no, you are debating that the true mean is $37,318, and you haven't even brought the evidence to support it. You don't even have evidence to support it. Level significance was step 2, level significance, 5%. Okay. Third step, so we're filling in that space in the lecture notes. There should be a slide where you fill this in. But I'm putting it up right now. Observe test statistic. So this is step 1. Here's step 2. Third step is to calculate the observed test statistic. So x bar minus mu over s divided by the square root of n. And again, remind me, I want to make sure y'all understand the difference between these variables. What is this? What is that? Sample mean, correct. That's the mean that we calculated using the 17 observations, the 17 data values. Is everybody with me? What is that? Population mean, right? And that value is always here. Is everybody with me? So what you're arguing over? 37,318. So let's do that. What was the sample mean? It tells you there. 34,223. $34,223. I'm gonna go to the nearest penny and 41 cents. Minus mean 37,318 divided by, what is this?
Sample standard
Sample standard deviation. Oh, go girl, you on fire. Sample standard deviation. Where's that over there? Oh, it doesn't give it. However, hold on. However, it gives the whole denominator. It gives the whole denominator. You see what it says standard error, STDERR? That's standard error. That's the value of all of this. Is everybody with me so far?
You gave us the sample standard deviation.
Oh, I did?
Yeah.
Oh,
Didn't you? On
yes.
the next page,
Oh, did
right?
I? Yes, I did. You're right. How can we show that's the sample standard deviation? Stay right there for just a second. Let me show it to you. Y'all know how to do descriptive. Y'all remember how to do descriptive statistics? Y'all remember that? You remind me. You remind me. Where do we click on to get like mean, standard deviation, all that stuff? Remember stat, summary stat. Oh my God. Yes. Hold on. Stop. Just me and you, because you on fire. You just shooting no free throws. Stats, summary stats. What?
Rows?
No.
Columns?
Columns. Yes, columns. And then total winnings. And I think it gives it to you by default. And then hit compute. There it is. Standard deviation. It's right there. See it? $16,108.75. You see that? So look, so and then so if we do, and there's n sample size. So if we do me a favor. Somebody get your calculator. Can you take this value, $16,108.75, divided by square root of 17? So let me write that. Hold on. Let me write that down.
Square root of 17.
Yeah, hold that value. $16,108.75
Yes.
divided by square root of 17. That's the same thing as saying 34,223.41 minus 37,318 divided by. Hold on. Okay, now let's go. Oh. Okay. What was that value? The $16,108.75 divided by square root of 17? Was it this value?
39.0. Yeah.
See? So standard error gives you the entire denominator. That S over square root of n, this is called the standard error. But the S by itself is sample standard deviation. Is everybody with me? Yeah. So I'm going to put that value, 3906. So the denominator is equal to 3906.95. Thank you. And so if you calculate all that out, you will get the T that's over there, negative 0.792. Now, notice that T, I'm going to 3 numbers after the decimal. Okay? In statistics, in my culture of statistics, T is rounded to 3 numbers after the decimal. Z is rounded to 2 numbers after the decimal. Is everybody with me? Now, remember, if you forget that, if you always go out to how many numbers after the decimal?
4.
4, you're okay. Okay, so when in doubt, you can just go 4 numbers after the decimal, you'll be okay. So our observed test statistic is negative 0.792. All right? Now, how do we get the p-value? Okay, they got p-value of 0.78. Oh, by the way, let's show you those graphs. Here. See, there it is. See? So it tells, So it tells you, so here's the T distribution. It tells, I don't know why they put X here. I don't know why. So here's the T distribution. So negative 0.792 is somewhere like right, yeah, because negative 2, negative 4, negative 3, negative 2, negative 1. Yeah, that's right. So negative 0.792 is right here. And remember, to find the p-value, we're doing a right-tail test. You have to find the probability to the right. Is everybody with me? So when you do that, that's this shaded region. You see what I'm saying? But nonetheless, if we were doing right tail test, the upper 5% of this distribution, I think is somewhere about right here, is my guess. I think it's here. Anyway, it's somewhere, I think that's about 5%, the upper 5%. As you can see, if negative 0.792 is here, it's not in the rejection region. You see what I'm saying? Which is why we failed to reject the null hypothesis. All right? And then I'll show you just the others, just to go back down memory lane. So what is that? That's histogram, right? That's the histogram. And this green line is just telling you where the mean is. See, if you put your mouse over the green, that green line, it'll tell you what the mean was. See, 34,223. Okay. By the way, what's the shape of this? It's approximately what?
Right skew.
Right skewed, correct. It's almost right skewed. It's looking like it's trying to slope in that direction. That's right. All right. What is that? Dot plot, right? Okay. Now, of course, it's in this case, I think it's not doing it by. I gotta see. Let me see. Let me put a mouse over there. 33,673. There's the 33,714. So I think it's clustering it by the hundreds. Okay. The dot plot is not the best graph to look at here. Okay. It's not the best one to use for this because the data is very spread out since we're going to 5 digits. Okay. The one that if you wanted to use a graph to summarize this data, I would either use the histogram. I wouldn't use a dot plot. Unless you had some repeated data values, then I would use the dot plot. What you should use is the box plot. Remember we covered the box plot? And what did we talk about? Yeah, this shows evidence of right skew. Because remember, what did I tell you? If look at this. So, look at this. I said that if this is longer, right? If this is longer than that one, see, this is evidence of right skew right here. Okay? Now, this here, to me, this is showing kind of bimodal. So you got a good chunk of data here, and then because this is right, so you got another good chunk of data happening later. Remember, we saw it was going up, it slightly went down, then it went back up, and then it skewed to the right. You see what I'm saying? Kind of bimodal data there. So, but this shows a little bit of evidence of some skewness, because this is much longer than this. Okay? And then I think there was one more. Yeah, normal probability plot. Yeah. Mm-hmm. Somewhat around that line. It's flirting with that line a little bit. You had your hand up. Go ahead.
Yeah. So we get to use like examples of like these graphs for our project.
Yes.
Is what I'm assuming.
Yes.
Okay.
So you enter your data, you do whatever hypothesis you need, and then you have to take the output, print it, and attach it to the back of the worksheet.
So for each of these graphs, like it's better to choose like a one that symbolizes
your data,
your
correct.
data
That will best represent your data.
Okay.
Now, let me say this. I do not recommend when you choose when you make your graphs, don't use the hypothesis test, the graphs from the hypothesis test. Make them using the way I showed you, like which is the graph, like bar plot or graph, histogram. Use it from these menus, because remember when you make the graph, what do you have to put on it?
Oh, the title?
The title. Oh, good God Almighty, you're on fire. Yes, remember you got to put a title and you have to label your axes, right? So I would recommend that you use the graph features to make those graphs, okay? Or if you have to make a table, what do? We did stat, then we do stat, tables, frequency, or contingency table. You use contingency, whichever one. Is everybody with me so far?
Mm-hmm.
Yeah, use those. Don't use the graphs that are through the hypothesis test. All right. But nonetheless, what happened to the output? What happened to the, here it is. There, brush it.
Thank you.
Yeah. Let's go back to the,
Thank you.
yes. Okay. Oh, Chloe, you missed a lot. Don't tell her. Don't tell her anything.
Oh, it's her?
Yeah, we're going Sizzler. We're going Sizzler. We're going Sizzler. All right, so we'll tell you later.
So I try to come as fast as possible. I'm so sorry.
No, ain't no problem. We'll tell you later. We'll tell you later. They know something that you don't know. We'll tell you later. Okay. All right. So yeah, it's something. So that's the observed test statistic, and then that's the critical test statistic. So that means if this value, if the observed test statistic had it gone past 1.746, we would have rejected the null hypothesis. Is everybody with me? We're nowhere near it. Okay. Yeah. Let me finish that up. Let me just go ahead and wrap this up.
So even though it's nowhere near, it's still not rejecting it?
Right. We're failing to reject. That's right.
Okay, so
That's
it
right.
is failing to reject, and
Yes.
it's just also not near it at all.
Correct. Yeah, it's nowhere near it. Yeah, we're gonna end up failing to reject. So we didn't calculate degrees of freedom, did we?
No.
Okay, degrees of freedom is equal to n minus 1, which is 17 minus 1, or what? 16, right? And then the p-value is the probability to the right of our observed test statistic here. Negative 0.792. Which we see it is 0.78. It came out 0.78. Okay? Or approximately 0.78. Now, here's what I was going to tell you with the table. If we were to use the t-table, if we actually use the t-table, here's the complication with that. Oh. Okay, she on the roll, but she's sneezing.